Section: Introduction. In this section, we explore how large language models, LLMs, can enhance their problem-solving abilities by increasing the number of output tokens or calls. By doing so, LLMs improve reasoning, planning, self-reflection, and collaboration among agents. This allows agents to tackle complex tasks like browsing the web, fixing GitHub issues, and solving challenging math problems. We note a shift from static LLM applications to dynamic agentic programs, which are workflows represented as directed acyclic graphs, DAGs, that include LLM calls and external inputs like tool calls or human interactions. We recognize that the pattern of LLM calls emerges during runtime, making it hard to predict the entire workflow in advance. Single-threaded programs vary in length based on user prompts and the sequence of LLM calls, while multi-threaded programs form DAGs with different sequences of calls. Techniques like Monte Carlo tree search, MCTS, are commonly used for reasoning and planning in web-based agents. Current LLM serving engines, such as VLLM, focus on optimizing individual calls but often overlook the broader context of program dependencies, leading to inefficiencies. For example, under a first-come, first-served policy, long calls can block shorter ones, resulting in significant waiting times. To mitigate this, we propose preemptive scheduling methods like multi-level feedback queue, MLFQ, which can reduce blocking but still struggle with delays caused by older programs. Our solution, Autellix, is designed to prioritize LLM calls based on the total execution time of their programs, allowing shorter programs to complete first and reducing overall wait times. Autellix introduces a framework that uses program-level statistics to enhance scheduling and throughput. We present two scheduling algorithms, PLOS for single-threaded programs and Atlas for multi-threaded programs. These algorithms prioritize calls based on their cumulative execution times, improving efficiency and reducing delays. Given the high demands of programs with many LLM calls, Autellix also distributes calls across multiple engines. We observe that calls within a program often share common data, allowing us to optimize data locality and reduce unnecessary recomputation. We have implemented a prototype of Autellix that integrates with existing LLM serving engines and offers a stateful API for persistent sessions. Our evaluations show that Autellix significantly improves throughput compared to current systems. In summary, our contributions include formalizing agentic programs as dynamic DAGs, utilizing program-level statistics for scheduling, implementing effective load balancing across engines, and providing a deployable system that integrates seamlessly with existing frameworks while achieving notable throughput gains. Section Summary. In this section, we introduce Autellix, an LLM inference system designed to optimize the execution of dynamic agentic programs represented as directed acyclic graphs, DAGs, by prioritizing LLM calls based on program-level statistics, thereby reducing wait times and improving throughput. Our approach leverages non-clairvoyant scheduling algorithms and effective load balancing across multiple engines, resulting in significant performance enhancements compared to existing systems. Section: Background and related work. In this section, we provide an overview of the context for Autellix, focusing on the emerging AI agent infrastructure and its applications, which we divide into the LLM serving layer and the higher-level agentic layer. For the LLM serving layer, we explain that large language models, or LLMs, which power chatbots and AI applications, mainly use the transformer architecture. The inference process for LLMs occurs in two steps. First, the prefill phase, where the input prompt is transformed into intermediate token states, and second, the decoding phase, where new tokens are generated one at a time based on previous tokens. To speed up this process, LLM serving systems use a KV cache to store these intermediate states. LLM serving systems also handle the routing and execution of LLM calls. Recent advancements in this area draw from traditional operating system concepts like memory management and scheduling. For example, systems like VLLM use virtual memory techniques to minimize cache fragmentation and improve efficiency by sharing memory across requests. They also enhance GPU performance to speed up processes like self-attention and optimize scheduling to reduce response times. Overall, these techniques focus on optimizing individual LLM requests, while Autellix aims for broader program-level optimizations, particularly in scheduling. Moving to the agentic layer, we describe how developers create complex agentic programs that manage interactions between agents, tools, and humans. These LLM agents consist of a system prompt that defines their role and the LLM model they use. Agentic programs can either make LLM calls or handle external interruptions, allowing them to interact with various tools and APIs to control environments like databases or robotic systems. Frameworks like LangChain and Autogen help developers manage the flow of these programs, using programming concepts like conditionals and loops, while maintaining a history of interactions. We also highlight that agentic applications go beyond simple chatbots, automating tasks like web navigation, issue resolution, and fact-checking. These applications often scale their performance by employing techniques such as step-by-step reasoning, planning, and multi-agent collaboration. For instance, a single-threaded React agent uses chain-of-thought methods for efficient action, while multi-threaded programs like Monte Carlo tree search incorporate various strategies to find optimal solutions. Given the unpredictable nature of LLMs, agentic programs are dynamic, non-deterministic, and distributed. Thus, Autellix operates without prior knowledge of the workloads or execution patterns of these programs. Section Summary. In this section, we provide an overview of the AI agent infrastructure, highlighting the LLM serving layer, which optimizes token generation and resource management, and the agentic layer, where developers create programs that orchestrate interactions between agents and tools. We emphasize that Autellix focuses on program-level optimizations and operates without prior knowledge of workloads, enabling dynamic and non-deterministic execution of complex tasks. Section: Motivation. In this section, we discuss the motivation behind our work. Today, the infrastructure for AI agents separates large language model, LLM, serving systems from the programs that use them. As organizations move from simply responding to LLM queries to developing more advanced AI applications, it becomes essential for LLM engines to focus on program-level goals, such as response times and overall latencies. We define the end-to-end latency of a single-threaded program as consisting of three parts. 1. Waiting time, which is the total time spent queuing LLM calls. 2. Execution time, the total time taken to process those calls. And 3. Interceptions, which is the time spent waiting for external inputs like tool calls or human responses. Since interceptions are not related to LLM serving, we focus on identifying ways to reduce waiting and execution times, which we will address in the design of our scheduling policies. We observe that in various agentic workloads, such as chatbots and specific programs, most of the time is spent waiting as the load increases. Therefore, we prioritize minimizing wait times, which not only enhances program latencies but also boosts the throughput of the LLM engine. By completing calls faster, programs can make subsequent calls more quickly, increasing the overall rate of LLM requests. One challenge we face is call-level head-of-line, whole, blocking, where longer LLM calls delay shorter ones, leading to increased wait times. This is particularly evident in engines like VLLM, which must wait for ongoing calls to finish before scheduling new ones. We find that whole blocking is significant in workloads with long-tailed distributions of decoding steps. To measure this, we analyze the ratio of waiting time to execution time for different workloads. We discover that preemptive scheduling, similar to how operating systems manage long-running processes, can help reduce whole blocking by prioritizing shorter calls. Another challenge is program-level whole blocking, where longer programs with many LLM requests can delay shorter programs. Current LLM schedulers do not consider the overall program context, leading to inefficient scheduling decisions. Our evaluation shows that when the number of LLM calls is small, both first come, first served, FCFS, and preemptive policies like multi-level feedback queue, MLFQ, result in higher wait times for shorter programs. Without considering the program context, MLFQ may inadvertently starve shorter programs by prioritizing new requests from longer ones. We also find that a program's execution time is heavily influenced by how well the LLM engine handles the prefill and decoding phases. In workloads with long prefills, we focus on optimizing prefill performance through prefix caching, which allows us to store and reuse relevant key-value cache entries across LLM requests. Our analysis of cache hit rates shows that within a single program, these rates remain high, indicating that LLM calls share similar contexts. However, when comparing different programs, the cache hit rate decreases with input length, suggesting that only the system prompt is shared. These findings highlight the importance of considering data locality in LLM serving systems, as much of the cache can be reused for future requests. Section Summary. In this section, we highlight the need for LLM engines to optimize for program-level objectives by addressing issues of waiting and execution times, particularly focusing on reducing head-of-line blocking and improving prefill performance through techniques like prefix caching. Our findings indicate that efficient scheduling and data locality can significantly enhance throughput and reduce latencies in agentic workloads. Section: Autellix Design. In this section, we present the overall architecture of Autellix and delve into its two main components. 1. A scheduler that is aware of program needs, aimed at reducing blocking at both the call and program levels, and 2. A load balancer that considers data locality. Autellix serves as a higher-level engine tailored for agentic programs rather than just individual requests. Our focus is on three key goals. 1. Enhancing the end-to-end latency for users. 2. Maximizing GPU usage for providers. And 3. Reducing program starvation to ensure fairness, which we measure using the 95th and 99th percentile latencies. We assume that Autellix does not have prior knowledge of when programs will arrive, how workflows are structured, or the general distribution of workloads. When a program comes in, its execution structure is initially unknown, so Autellix builds an internal representation dynamically as the program runs. This adaptability allows Autellix to work with any program that makes calls to the underlying engine. Unlike previous systems that fit static applications, we assume users run general Python programs locally that connect to Autellix's backend. Our architecture is distinct because, unlike existing engines that treat calls as stateless, Autellix maintains state. Programs run from the user's machine, create a session with Autellix, and make calls over time, each associated with a session ID. When a session begins, we add an entry to a global process table that tracks important program details, such as total service time, thread metadata, and waiting times for LLM calls. Both the scheduler and load balancer utilize this table to manage LLM calls effectively. We introduce a program-aware scheduler designed to minimize response times without needing prior knowledge. To reduce blocking, Autellix prioritizes calls based on program statistics and can dynamically preempt calls. For effective prioritization, we rely on a global process table that records key metrics for all running programs. This table helps us make better scheduling decisions for both single and multi-threaded programs. Each entry in the table tracks service time, waiting time, engine IDs, thread metadata, and the most recent call arrival and completion times. For single-threaded programs, we use the least attained service (LAS) algorithm, which is effective in settings where we lack exact knowledge of runtimes. We extend this to create program-level attained service (PLOS), which assigns priorities based on the total runtime of previous calls. This approach helps shorter programs finish sooner, reducing overall response times. In contrast, multi-threaded programs are represented as dynamic directed acyclic graphs (DAGs) of calls. The completion time is determined by the longest sequence of dependent calls, known as the critical path. To optimize scheduling, we introduce Adaptive Thread Level Attained Service (ATLAS), which prioritizes calls based on their service times along the critical paths. ATLAS maintains a record of the longest observed critical path for each program, allowing it to refine priorities dynamically without tracking all dependencies. This method ensures that programs with shorter critical paths are favored, effectively grouping parallel calls to prevent delays in program completion. Section Summary. In this section, we present Autellix's architecture, which includes a program-aware scheduler and a data locality-aware load balancer, aimed at enhancing end-to-end latency, maximizing GPU utilization, and reducing program starvation. We describe how Autellix dynamically constructs an internal representation of programs, tracks their execution metrics through a global process table, and employs innovative scheduling algorithms like PLOS and Atlas to prioritize LLM calls based on service times and critical paths, all while operating under non-clairvoyant assumptions. Section: Preemptive Scheduling. In this section, we discuss preemptive scheduling in Autellix, where we assign priorities to each LLM call based on the program's history. We recognize that using continuous priorities can lead to inefficient round-robin scheduling, which can perform worse than first come, first served, FCFS, and cause unnecessary context switches, including frequent transfers between CPU and GPU. To address this, we discretize priorities into a limited number of queues, similar to multi-level feedback queues, MLFQ, used in operating systems. We categorize LLM calls into K queues, where priorities decrease from the highest queue to the lowest. Each queue covers a specific range of priorities, starting from 0 for the highest queue and extending to infinity for the lowest. When a new LLM call arrives, we check its priority based on the process table. Unlike traditional MLFQ, where all new calls start at the highest priority, we assign calls to the appropriate queue based on their discretized priority. Calls then execute in FCFS order within their assigned queue. If a call uses up its time quantum, it is moved to a lower priority queue. To prevent long waits, we implement anti-starvation mechanisms, which we will describe next. Once a call finishes decoding, it updates the process table. We also address the issue of starvation that can occur with discrete prioritization. Simple techniques, like promoting calls that have waited too long, can lead to naive MLFQ behavior, where long-running calls interrupt shorter ones. To avoid this, we use the process table to monitor program-level starvation. Specifically, we promote a call to the highest priority queue if its total waiting time compared to its service time exceeds a certain threshold. Adjusting this threshold balances average response times and fairness among programs. In terms of memory management, we face challenges with the high volume of concurrent LLM calls, which leads to frequent transfers between GPU and CPU. Previous methods have tried to reduce this overhead by preemptively swapping KV cache blocks. However, since Autellix requires real-time updates, we implement two optimizations to minimize both the frequency and overhead of these swaps. First, we schedule the LLM calls every n decoding steps instead of at every step, allowing us to manage queued requests more efficiently. Second, we use a more effective GPU-CPU swap kernel that gathers all KV blocks into a single buffer for transfer, which enhances bandwidth and reduces latency. Finally, as workloads scale, we find it necessary to deploy multiple engine replicas. However, we must consider data locality to optimize performance. Our analysis shows that short requests, which are under 2048 tokens, have high cache hit rates across any engine, so we balance these requests across the least loaded engines. In contrast, longer requests benefit from being routed consistently to the same engine due to their significant prefix overlap, which reduces recomputation. We dynamically route short requests to the least loaded engine while keeping longer requests tied to their respective engines. Our evaluation demonstrates that this load balancing approach improves both throughput and latency across various workloads. Section Summary. In this section, we describe how Autellix implements preemptive scheduling by discretizing LLM call priorities into multiple queues to avoid inefficiencies like context switching and starvation. We also detail our memory management optimizations to reduce GPU-CPU swapping and a load balancing strategy that dynamically routes short and long requests based on data locality to enhance performance. Section: Implementation. In this section, we describe the implementation of Autellix, a system designed for serving multiple large language model (LLM) inferences. Autellix consists of a front-end, a scheduler, and a load balancer, totaling around 5,000 lines of code written in Python and CUDA, C++. For the front-end, we extend OpenAI's chat completion and Vilm's Python APIs to create a user-friendly interface that feels stateless to developers. Users can easily integrate Autellix into their Python applications. When a program starts, Autellix automatically sends a request to begin a session, which generates a unique session ID and logs it in a process table. Each subsequent LLM call is tagged with the relevant session, program, and thread IDs before being sent to the backend. Once the program finishes or encounters an error, we call an end session function to remove the entry from the process table. As this is a research prototype, we acknowledge that the front-end currently lacks protections against user modifications, which we plan to address in future work. For the LLM engine, we build on VLLM version 0.6.1. We focus on modifying the scheduler by adding new policies and memory management techniques to enhance efficiency. This approach allows us to conduct experiments easily and clearly identify performance improvements. We also noticed that in VLLM, each key value block is transferred separately, which can lead to inefficiencies. To improve this, we create a host buffer to combine all key value blocks into one large transfer, which optimizes the process. Regarding multi-engine capabilities, VLLM does not currently support managing multiple LLM engines simultaneously. To test our load balancing strategy, we developed async multi-LLM engine on top of async LLM engine. Each LLM engine runs in its own Python process, coordinated by a meta-engine that uses standard inter-process communication methods. When the meta-engine receives a request, it assigns it to the appropriate engine and returns a future-like object to the front-end without waiting. The selected engine processes the task asynchronously and sends the result back through the communication channel. This setup allows us to handle multiple requests in parallel, with the meta-engine efficiently managing routing and resource allocation. In our evaluation, we analyze various agentic workloads to assess Autellix's performance compared to leading LLM serving systems and to examine our design choices. We conduct real-world experiments using 4 distinct workloads that differ in the number of tokens and LLM calls. The first workload, ShareGPT, consists of user-generated conversations typical for chatbots. It has a long-tailed distribution of LLM calls, averaging about 6.66 calls per conversation, with a maximum of 80. The calls are decode-heavy, averaging 277 decode tokens compared to 256 prefill tokens, as short prompts lead to detailed responses. The second workload, BFCL, evaluates LLMs on multi-turn tasks. It has a mean of 10.75 calls per program and a maximum of 70. This workload is prefill heavy, with an average of 735.06 tokens per call due to extensive system prompts, while decodes are shorter, averaging 34.14 tokens. The third workload, LATS, involves running Monte Carlo tree search on Hotpot QA, which is computationally demanding and includes many parallel LLM calls. Each instance averages 159.7 calls, significantly more than the previous workloads, with prefill and decoding phases averaging 467.2 and 72.6 tokens, respectively. Finally, we create a mixed workload by sampling equally from all 3 previous workloads to test Autellix's performance under diverse conditions. We generate program arrivals using a Poisson process to simulate real-world scenarios accurately. Section Summary. In this section, we describe the implementation of Autellix, a multi-engine LLM inference serving system that integrates a front-end, scheduler, and load balancer, allowing for efficient management of LLM calls through a stateful interface and enhanced scheduling policies. We also evaluate Autellix's performance across diverse real-world workloads, including chatbot interactions and computationally intensive tasks, to demonstrate its capability in handling multiple concurrent requests effectively. Section: Experimental Setup. In this section, we describe our experimental setup and the models we evaluated. We used 3 models: Llama-3.1-8B, 70B, and Falcon 180B, running on 1, 4, and 8 GPUs, respectively. Our experiments took place on a GCP compute engine instance equipped with 8 A100S XM4-80 GB GPUs, connected through NVLink, with 1,360 GB of host memory, PCIe 4.0x16, and 2 TB of disk space. For metrics, we noted that existing large language model, LLM, serving systems focus on request-level metrics like time to first token and time per output token, which we refer to as token latency. However, these metrics do not account for the overall latency in agentic programs. Therefore, we introduced a new metric called program-level token latency, which is the total response time of a program divided by the number of tokens generated. A system designed for high throughput should maintain low program-level latency even under high request rates, and we will refer to this metric simply as latency throughout our evaluation. We considered 3 baselines for our evaluation, all using the same maximum batch size. The first baseline, VLLM, is a leading high-throughput LLM serving system that employs continuous batching and paged attention to minimize cache fragmentation. Its default scheduling policy is first come, first served, which is not aware of application needs and can lead to blocking issues. We used version 0.6.1 of VLLM. The second baseline, VLLM opt, is an optimized version that includes features like chunk prefill and prefix caching, closely matching the performance of other systems like SGLang and TensorRT. The third baseline, MLFQ, builds on VLLM opt and adds preemption through the multi-level feedback queue algorithm to address blocking issues. For end-to-end single-engine performance, we compared Autellix against the 3 baselines across 4 workloads: Share GPT, BFCL, LATS, and Mixed. Autellix consistently achieved the highest throughput with the same token latency across all workloads. In contrast, VLLM performed the worst due to its lack of prefix caching, leading to costly recomputation for LLM calls within the same program. The performance of VLLM opt and MLFQ varied depending on the workload. For single-threaded workloads like Share GPT and BFCL, VLLM and VLLM opt experienced significant blocking, increasing latencies as request rates rose. MLFQ improved throughput by 1.5 times over VLLM opt but still faced issues under high load. By using our PLOS approach to address both types of blocking, Autellix achieved up to 8 times the throughput of VLLM and twice that of VLLM opt. In the multi-threaded LATS workload, Autellix outperformed the other systems by up to 5 times. MLFQ's preemptive scheduling, which helps single-threaded programs, was less effective in multi-threaded scenarios, as it disrupted threads and worsened blocking. Autellix's Atlas policy optimized resource allocation across all threads, ensuring balanced progress and high throughput. For mixed workloads, Autellix achieved up to 15 times higher throughput than VLLM, 5.5 times higher than MLFQ, and 4 times higher than VLLM opt. As the diversity of LLM calls and decode lengths increased, Autellix's ability to reduce blocking led to better performance. Regarding tail latency, we found that while preemptive scheduling can lower average latency, it may increase tail latency by affecting long-running programs. We reported the 95th and 99th percentile latencies for different workloads on LLAMA 3.1 to 8B. For Share GPT, MLFQ improved average latency compared to VLLM opt but had poor tail latencies. For BFCL, MLFQ outperformed VLLM opt in both metrics. Overall, in 7 out of 8 scenarios, Autellix maintained lower tail latencies than both MLFQ and VLLM opt, improving throughput by up to 1.7 times for tail latencies, demonstrating strong performance in both average and tail metrics. Section Summary. In this section, we evaluate the performance of our model, Autellix, against three baselines, VLLM, VLLM opt, and MLFQ, across various workloads, demonstrating that Autellix consistently achieves the highest throughput and lowest latency, particularly under heavy load and multi-threaded conditions. We also highlight that Autellix effectively reduces both program and call level blocking, maintaining superior performance in average and tail latency metrics compared to the other systems. Section: End-to-end multi-engine performance. In this section, we evaluate the performance of Autellix's data locality-aware load balancer by comparing it to two common load balancing methods, round-robin and least used, under the same scheduling policies. Round-robin assigns requests to engines in a cyclic manner, which ensures an even distribution but ignores data locality, leading to costly cache misses and high recomputation. Least used directs requests to the engine with the fewest calls, balancing workloads but also neglecting data locality, resulting in frequent recomputations. We conduct experiments using 4 replicas of the Llama 3.1-8b model and 2 replicas of the Llama 3.1-70b model with shared GPT and LATS workloads. Our results show that Autellix maintains low average and tail latencies across all configurations, achieving up to 1.4 times higher throughput compared to both baseline methods. This advantage is particularly noticeable with the shared GPT workload, where reusing chat history enhances cache locality. As we increase the number of replicas, the benefits become even clearer, as a larger engine pool reduces the chances of requests being sent to engines that lack locality. To assess Autellix's scalability, we analyze its performance as we increase the number of engine replicas under different latency requirements, specifically using the shared GPT workload with the Llama 3.1-8b model. Our findings indicate linear scaling in all scenarios. By utilizing program-level load balancing, Autellix scales effectively without the overhead of data locality, making it a strong choice for large-scale deployments. We also perform ablation studies on Autellix in various scenarios, including offline batch inference, timing breakdowns, and different design choices like the swap kernel. In offline settings that prioritize throughput, we process large batches of programs at once. Our analysis shows that Autellix consistently outperforms the baselines, reducing the average makespan by 10 to 40%. Notably, at 4,000 programs, the MLFQ method fails to complete execution due to overwhelming memory contention and frequent GPU-CPU swapping, leading to out-of-memory errors despite having a large swap space. We break down the time spent on LLM calls in the serving layer for Autellix and its baselines. Overall, Autellix achieves lower token latency for both shared GPT and LATS by minimizing wait and swap times, thanks to its scheduling policy and improved swap kernels. Although both Autellix and MLFQ have higher scheduling times than the naive first-come, first-served method, Autellix incurs lower overhead by effectively distributing calls across different priority queues. When comparing to optimal scheduling methods like shortest remaining processing time, which assume complete knowledge of program runtimes, we simulate this scenario by revealing each program's total calls and decode steps beforehand. Under these conditions, Autellix outperforms first-come, first-served and other preemptive schedulers, though a gap remains compared to the optimal method, indicating that prior knowledge can significantly enhance performance. Finally, we address the impact of the swapping kernel. Preemptive scheduling increases the number of active LLM calls, leading to high GPU memory usage and frequent GPU-CPU swaps. Autellix reduces this issue by batching KV block transfers into a single operation, cutting down swaps by up to 18 times and swap times by 3 to 7 times, achieving 1.3 times higher throughput than the kernel implemented in VLLM. Section Summary. In this section, we evaluate Autellix's data locality-aware load balancer against traditional strategies like round-robin and least used, demonstrating that Autellix significantly reduces latencies and increases throughput, up to 1.4 times higher, especially in workloads that benefit from cache locality. Our experiments show that Autellix scales effectively with more engine replicas and outperforms baselines in both offline batch inference and timing breakdown, while also minimizing swapping overheads through efficient KV block transfers. Section: Discussion and Future Work. In this section, we discuss graph optimizations and future work. Autellix does not rely on prior knowledge of a program's execution-directed acyclic graph, DAG. Instead, we build this graph dynamically during runtime. While knowing every detail of a program's execution is not feasible, predicting its next steps can be useful. This allows us to implement compiler optimizations like branch prediction and speculative execution, which lets future large language model (LLM) calls run while previous ones are still finishing. We plan to explore these optimizations in future research. Regarding post-training, we utilize reasoning models like DeepSeek R1 and OpenAI's O1-O3 models, which undergo post-training through end-to-end reinforcement learning (RL) to enhance their reasoning abilities. To speed up training, our distributed RL systems alternate between sampling and training to gather data and update policies. By improving our scheduling, Autellix minimizes the total time needed for batch sampling in each RL iteration, which directly benefits our distributed post-training systems.